Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Between the crimson deserts of Mars and the swirling storms of Jupiter lies a vast expanse that has captivated astronomers for over 2 centuries. The asteroid belt, stretching across millions of miles of space, represents one of the solar system's most fascinating yet misunderstood regions. Far from the dense, chaotic demolition derby often depicted in science fiction, this cosmic neighborhood holds secrets that reveal the very origins of our planetary system. The story begins on New Year's Day, 1801, when Italian astronomer Giuseppe Piazzi peered through his telescope and spotted what he initially believed was a new comet. This celestial object, later named Ceres, became the first asteroid ever discovered. Within 6 years, astronomers had identified 3 more similar objects, Pallas, Juno, and Vesta, all orbiting in the same general region between Mars and Jupiter. The pattern was unmistakable. A previously unknown population of rocky bodies inhabited this distant frontier. Early 19th century astronomers faced a puzzle. These objects were too small to be planets, yet too numerous to be mere oddities. The German astronomer Heinrich Olbers proposed a revolutionary theory. Perhaps these fragments were remnants of a destroyed planet that once orbited between Mars and Jupiter. This exploded planet hypothesis captured imaginations for decades, painting the asteroid belt as a cosmic graveyard, marking the violent death of an entire world. Modern science has revealed a far more nuanced truth. The asteroid belt contains between 1.1 and 1.9 million asteroids larger than half a mile in diameter, with countless smaller fragments filling the spaces between. Yet, despite this enormous population, the total mass of all asteroid belt objects combined equals roughly 4% of our Moon's mass. If you could somehow gather every asteroid into a single sphere, it would measure less than 900 miles across, smaller than many of Earth's continents. The Ceres belt's sparse nature becomes clear when considering its immense scale, stretching from approximately 2.2 astronomical units to 3.2 astronomical units from the Sun, where 1 astronomical unit equals Earth's distance from our star. The asteroid belt encompasses a volume of space so vast that typical distances between asteroids measure in millions of miles. Space missions routinely traverse this region without encountering a single rock, despite popular media's portrayal of navigational nightmares. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The asteroids themselves tell remarkable stories. Ceres, reclassified as a dwarf planet in 2006, contains about 1/3 of the asteroid belt's total mass. This ancient world harbors subsurface oceans and complex geology, challenging our understanding of where life might exist in the cosmos. Vesta, with its massive crater and basaltic surface, resembles a planet that never quite finished forming. These diverse worlds preserve 4.6 billion years of solar system history in their battered surfaces and varied compositions. Recent discoveries have revolutionized our perception of asteroid belt formation. Rather than fragments of a destroyed planet, these objects represent building blocks that never coalesced into a world. Jupiter's immense gravitational influence prevented accretion, leaving behind a museum of primordial materials. Some asteroids contain water ice, organic compounds, and rare metals that could fuel humanity's expansion into space. Others preserve pristine samples of the solar nebula from which all planets formed. Understanding the asteroid belt requires sophisticated mapping techniques that combine ground-based observations with spacecraft missions. Each discovery adds pieces to a cosmic puzzle that spans billions of years and millions of miles, revealing how gravitational forces, solar radiation, and collisional evolution shaped this remarkable region into the complex ecosystem we observe today. Mapping the asteroid belt presents challenges that dwarf terrestrial cartography. Unlike charting Earth's static continents, asteroid cartographers must track over 1 million moving targets across a region spanning hundreds of millions of miles. Each asteroid follows its own orbital path, tumbles through space at varying rates, and changes brightness as it rotates. Creating accurate maps of this dynamic environment requires innovative techniques that push observational astronomy to its limits. The modern asteroid census began with photographic surveys in the early 20th century, but computerized detection revolutionized the field. The linear program operated by MIT's Lincoln Laboratory uses automated telescopes to scan the sky repeatedly, comparing images to identify moving objects. By analyzing how points of light shift position between exposures, Linear can distinguish asteroids from background stars and calculate preliminary orbital parameters. The Catalina Sky Survey, operating from Arizona's Santa Catalina Mountains, has discovered over half of all known near-Earth asteroids. Their Schmidt telescopes capture wide-field images, covering enormous swaths of sky, enabling systematic searches that would be impossible with traditional narrow-field instruments. Advanced software processes thousands of images nightly, flagging potential asteroids for human verification. This assembly line approach to discovery has increased the known asteroid population from fewer than 10,000 in 1990 to over 1.3 million today. Space-based observations provide unique advantages for asteroid detection. NASA's Near-Earth Object Wide-Field Infrared Survey Explorer, or NEOWISE, detects asteroids by their thermal emission rather than reflected sunlight. This infrared perspective reveals size and composition information impossible to obtain from ground-based visible light observations. NEOWISE has characterized thermal properties for over 150,000 asteroids, creating the most comprehensive database of asteroid physical properties ever assembled. The European Space Agency's Gaia mission, primarily designed to map stars, has become an unexpected asteroid hunter. Gaia's extraordinary precision, capable of measuring stellar positions to within 10 microarc seconds, enables detection of asteroid motion with unprecedented accuracy. By observing the same regions repeatedly over its multi-year mission, Gaia has refined orbits for hundreds of thousands of asteroids while discovering thousands of new objects. Asteroid naming conventions reflect humanity's cultural diversity. The International Astronomical Union oversees naming rights, allowing discoverers to propose names for asteroids they find. Names honor scientists, artists, historical figures, and even fictional characters. Asteroid 2001 Einstein celebrates the famous physicist, while Asteroid 17173 jazz honors American musical traditions. These names transform sterile catalog numbers into memorable identities, connecting remote space rocks to human experience. Tracking asteroid orbits requires solving complex gravitational problems. Each asteroid experiences gravitational pulls from the Sun, planets, and even other asteroids. The largest asteroids exert measurable gravitational effects on smaller neighbors, creating subtle orbital perturbations that must be accounted for in long-term predictions. Advanced computer models incorporate relativistic effects, solar radiation pressure, and thermal forces that influence asteroid trajectories over millions of years. The Yarkovsky effect demonstrates how subtle forces shape asteroid orbits. When rotating asteroids absorb sunlight and re-emit thermal radiation, they create tiny but persistent thrust forces. This effect can alter orbital periods by minutes per year, causing dramatic changes over geological timescales. Understanding Yarkovsky acceleration enables astronomers to predict asteroid positions centuries into the future, crucial for assessing potential impact risks and planning space missions. Database management for asteroid observations requires sophisticated information systems. The Minor Planet Center, operated by the International Astronomical Union, serves as the global clearinghouse for asteroid observations. Every night, observatories worldwide submit measurements of asteroid positions, brightnesses, and colors. Automated systems process these observations, update orbital calculations, and distribute refined ephemerides to the global astronomical community. Modern asteroid surveys generate enormous data sets. The Legacy Survey of Space and Time, currently under construction in Chile, will photograph the entire visible sky every few nights for 10 years. This ambitious project will discover millions of new asteroids while monitoring brightness variations that reveal rotation periods, shapes, and surface properties. Managing and analyzing these vast datasets requires new approaches to astronomical data processing. The asteroid belt structure reveals one of nature's most elegant examples of gravitational choreography. Far from randomly scattered debris, asteroids occupy specific orbital zones determined by a complex interplay of forces that has persisted for billions of years. Jupiter, the solar system's gravitational heavyweight, serves as the primary architect of this cosmic arrangement, creating invisible boundaries that corral asteroids into distinct populations while leaving vast, empty spaces between them. Orbital resonances provide the key to understanding asteroid belt organization. A resonance occurs when an asteroid's orbital period maintains a simple ratio with Jupiter's 12-year orbit around the Sun. Asteroids in 2-to-1 resonance complete exactly 2 orbits for every 1 Jovian year, while those in 3-to-1 resonance complete 3 orbits in the same time. These mathematical relationships create zones where gravitational effects either stabilize or destabilize asteroid orbits over millions of years. The Kirkwood gaps, named after 19th-century American astronomer Daniel Kirkwood, represent regions almost entirely devoid of asteroids. These gaps occur at major resonances with Jupiter, where repeated gravitational tugs eventually eject asteroids from their original orbits. The most prominent gap occurs at the 2-to-1 resonance, located approximately 3.3 astronomical units from the Sun. Asteroids that drift into this zone experience periodic gravitational kicks that increase their orbital eccentricity until they intersect Mars or Earth's orbit, leading to eventual ejection from the asteroid belt. Between these gaps lie stable regions where asteroid populations thrive. The inner belt, extending from 2.1 to approximately 2.5 astronomical units, contains mostly S-type asteroids, rocky bodies composed primarily of silicate minerals and metallic iron. These objects likely formed in the warmer, inner regions of the early solar system before migrating to their current positions. Their relatively high albedo or reflectivity makes them easier to detect than their darker outer belt cousins. The middle belt, ranging from 2.5 to 2.8 astronomical units, represents the asteroid belt's most densely populated region. Here reside the largest asteroids, including Ceres, Vesta, and Pallas. This zone's stability allows accumulation of both rocky S-type asteroids and darker C-type asteroids, rich in carbon compounds and water-bearing minerals. The size distribution in this region suggests it has remained relatively undisturbed since the solar system's formation. The outer belt, extending beyond 2.8 astronomical units, contains predominantly C-type and P-type asteroids. These dark, primitive objects preserve organic compounds and water ice that would have been destroyed in the inner solar system's intense heat. Their low albedo and distant orbits make detection challenging, leading to significant observational bias in asteroid discovery surveys. Advanced infrared observations reveal that outer belt asteroids comprise a substantial fraction of the belt's total population. Secular resonances add another layer of complexity to asteroid dynamics. Unlike mean motion resonances involving orbital periods, secular resonances affect the long-term evolution of orbital shapes and orientations. The Noosic secular resonance creates a sharp boundary in the inner asteroid belt, preventing asteroids from maintaining stable orbits closer than approximately 2.1 astronomical units from the Sun. Chaotic zones within the asteroid belt demonstrate how small changes can produce dramatic long-term effects. Some asteroids follow trajectories that appear stable for millions of years before suddenly shifting into planet-crossing orbits. These chaotic regions challenge long-term orbital prediction and highlight the inherent unpredictability embedded within deterministic gravitational systems. The Yarkovsky-O'Keefe-Radzievsky-Paddock effect, known as the YORP effect, shows how thermal forces influence asteroid rotation and orbital evolution. Asymmetric thermal emission from irregularly shaped asteroids creates torques that can spin objects apart or alter their orbital trajectories over geological timescales. This effect couples asteroid rotation with orbital dynamics, creating feedback loops that influence long-term belt evolution. Asteroid families provide evidence of ancient collisions that shattered larger parent bodies. These groupings of asteroids share similar orbital characteristics and compositions, suggesting common origins. The Flora family, located in the inner belt, contains over 13,000 known members, derived from a collision approximately 1 billion years ago. Studying these families reveals the collisional history that has shaped the asteroid belt throughout solar system evolution. Computer simulations of asteroid belt dynamics require massive computational resources to track gravitational interactions among thousands of objects over millions of years. These models incorporate planetary perturbations, relativistic effects, and non-gravitational forces to understand how the current belt structure emerged from the solar system's chaotic early history. Humanity's first close encounter with an asteroid occurred almost by accident during Galileo's journey to Jupiter in 1991. As the spacecraft flew past asteroid 951 Gaspra, its cameras captured images revealing an irregularly shaped, heavily cratered world unlike anything previously imagined. This serendipitous flyby marked the beginning of dedicated asteroid exploration, transforming these distant specks of light into real worlds with unique personalities and complex histories. The Galileo mission's second asteroid encounter in 1993 provided even more revelations. Asteroid 243 Ida appeared accompanied by a small moon, later named Dactyl, making it the first known binary asteroid system. This discovery challenged assumptions about asteroid formation and evolution, suggesting that gravitational, capture or impact events could create multiple body systems even among relatively small objects. Ida's elongated shape and ancient surface, revealed by crater counting, indicated an age exceeding 1 billion years. ASA's Near-Shoemaker mission achieved the first asteroid orbital insertion in February 2000, beginning a year-long study of 433 Eros. This S-type asteroid, measuring approximately 21 miles long, displayed unexpected complexity despite its modest size. High-resolution imaging revealed layered deposits, boulder fields, and evidence of space weathering that darkened the surface over geological time. NEAR's gamma-ray spectrometer detected variations in elemental composition across Eros's surface, indicating a heterogeneous interior structure. The mission's dramatic finale saw Near-Shoemaker attempt the first controlled landing on an asteroid's surface. Though not designed for surface operations, the spacecraft transmitted images during its descent, revealing details smaller than 4 inches across. The successful landing demonstrated that asteroid surfaces could support spacecraft operations, paving the way for future sample return missions. Japan's Hayabusa mission tackled the ambitious goal of collecting samples from asteroid 25,143 Itokawa and returning them to Earth. Launched in 2003, Hayabusa faced numerous technical challenges during its 7-year journey. Ion propulsion system failures, communication blackouts, and fuel leaks threatened the mission's success, yet innovative engineering solutions kept the spacecraft operational. Itokawa proved to be a fascinating target. This small, elongated asteroid displayed a bimodal surface with both rough, boulder-covered regions and smooth areas covered in fine particles. The smooth regions, dubbed seas, suggested ongoing geological processes despite the asteroid's tiny size and presumed ancient age. Spectroscopic measurements confirmed Itokawa's classification as an S-type asteroid, linking it to ordinary chondrite meteorites found on Earth. Hayabusa's sample collection faced unexpected challenges when the spacecraft's sampling mechanism failed to fire properly. However, microparticles of asteroid material entered the sample container during brief surface contact, providing precious samples for laboratory analysis. When the return capsule landed in Australia in 2010, it contained over 1,500 particles of extraterrestrial material, the first samples returned from an asteroid. Laboratory analysis of Itokawa samples revolutionized understanding of asteroid evolution. The particles showed evidence of space weathering processes that alter asteroid surfaces over millions of years. Solar wind implantation, micrometeorite bombardment, and thermal cycling create complex chemical and physical changes that must be accounted for when interpreting remote sensing observations of other asteroids. NASA's Dawn mission employed innovative ion propulsion to visit two of the asteroid belt's largest objects, Vesta and Ceres. This ambitious mission required precise trajectory planning to enable orbital operations at both destinations, a feat impossible with conventional chemical propulsion. Dawn's 11-year journey provided unprecedented insights into asteroid belt formation and evolution. Vesta, the second most massive asteroid, revealed itself as a differentiated world with distinct geological provinces. A massive impact basin near the South Pole excavated material from deep within Vesta's interior, creating the distinctive topographic features visible in Hubble Space Telescope images. Dawn's detailed mapping revealed evidence of ancient volcanic activity, confirming that Vesta underwent planetary-scale geological processes during its formation. Ceres presented even greater surprises, bright spots within a crater initially. Puzzled scientists before spectroscopic analysis revealed deposits of sodium carbonate, evidence of past hydrothermal activity. Dawn detected water vapor emissions from Ceres's surface, confirming the presence of subsurface ice. These observations elevated Ceres from a simple asteroid to a complex world potentially capable of supporting microbial life. NASA's OSIRIS-REx mission achieved another milestone in asteroid exploration by successfully collecting samples from 101,955 Bennu. This carbon-rich asteroid provided insights into the early solar system's organic chemistry and water content. The mission's detailed reconnaissance revealed Bennu's surface to be much more rugged than expected, forcing mission planners to identify new landing sites among boulder fields and steep slopes. The successful sample collection from Bennu in 2020 demonstrated advanced autonomous navigation and sample acquisition techniques essential for future asteroid missions. When OSIRIS-REx returns to Earth in 2023, its samples will provide unprecedented insights into organic compound formation and water delivery to the early Earth. Asteroids preserve the solar system's most ancient materials, serving as time capsules that reveal conditions during planetary formation 4.6 billion years ago. Unlike planets, which have been modified by geological processes, many asteroids retain pristine compositions dating to the solar nebula's collapse. Understanding asteroid composition requires sophisticated remote sensing techniques that analyze reflected sunlight to determine mineralogy, surface properties, and evolutionary history. The asteroid classification system organizes these diverse objects based on spectroscopic properties and albedo measurements. C-type asteroids, representing approximately 75% of the known population, appear dark with albedos typically below 10%. These carbon-rich objects dominate the outer asteroid belt, where cooler temperatures during solar system formation allowed preservation of volatile compounds, including water ice and organic molecules. C-type asteroids likely originated beyond the snowline, where water could condense into ice grains that were incorporated into growing planetesimals. S-type asteroids comprise roughly 17% of the known population and show much higher albedos, typically between 10 and 22%. These objects display strong absorption features, indicating the presence of olivine and pyroxene minerals combined with metallic iron. S-type asteroids concentrate in the inner asteroid belt, consistent with formation in the warmer inner regions of the early solar system. Spectroscopic studies link S-type asteroids to ordinary chondrite meteorites, the most common type found on Earth. M-type asteroids represent a smaller but scientifically important population characterized by moderate albedos and relatively featureless spectra. Many M-type asteroids appear to be metallic, composed primarily of iron and nickel, similar to planetary cores. These objects may represent fragments of differentiated planetesimals that were disrupted by collisions, exposing their metallic interiors. However, some M-type asteroids show evidence for hydrated minerals, indicating more complex formation histories. Spectroscopic analysis relies on identifying specific absorption features in reflected sunlight that correspond to electronic transitions in minerals. The 1 micrometer and 2 micrometer absorption bands, diagnostic of pyroxene and olivine, allow astronomers to determine relative abundances of these key rock-forming minerals. Band depths and positions provide information about mineral compositions, while continuum slopes indicate space weathering effects and grain sizes. Space weathering processes gradually alter asteroid surface properties over millions of years. Solar wind particles implant into mineral grains, creating nanoscopic ion particles that darken surfaces and reduce absorption band depths. Micrometeorite bombardment pulverizes surface materials, creating fine-grained regolith that affects reflectance properties. Understanding space weathering is crucial for connecting asteroid observations to meteorite samples collected on Earth. Thermal emission spectroscopy provides complementary information about asteroid compositions. Different minerals emit characteristic thermal radiation patterns that can be detected using infrared telescopes. The Spitzer Space Telescope and ground-based facilities have measured thermal emission from hundreds of asteroids, revealing surface temperatures, thermal inertia, and compositional variations not visible in reflected light spectra. Asteroid densities, determined through gravitational perturbations during spacecraft flybys or by observing binary asteroid systems, provide insights into internal structure and porosity. Many asteroids show surprisingly low densities, indicating significant void space within their interiors. These rubble pile structures suggest that many asteroids represent gravitational aggregates of fragments created by collisional disruption of larger parent bodies. The distribution of asteroid types throughout the belt reveals thermal processing during solar system formation. The increasing proportion of C-type asteroids with distance from the Sun reflects the location of the snow line, where water ice could first condense in the cooling solar nebula. This compositional gradient provides observational evidence for theoretical models of planetary system formation. Primitive asteroids preserve organic compounds that may have contributed to life's origin on Earth. Spectroscopic detection of hydrated minerals and organic materials on C-type asteroids demonstrates that these objects contain the chemical ingredients necessary for biological processes. Impact delivery of organic-rich asteroid material during the late heavy bombardment may have provided early Earth with essential prebiotic compounds. Differentiated asteroids like Vesta experienced sufficient heating to melt and separate into distinct layers, creating metallic cores surrounded by silicate mantles and basaltic crusts. Eucrite meteorites, believed to originate from Vesta's surface, provide detailed insights into igneous processes on early planetesimals. These volcanic rocks demonstrate that some asteroids achieved planetary-scale geological evolution before cooling and solidifying. Recent discoveries of active asteroids that display comet-like behavior challenge traditional classification schemes. Objects like 3200 P Elst Pizarro show evidence of sublimation-driven activity, despite orbiting within the asteroid belt. These main belt comets may preserve pristine ice from the early solar system, offering new insights into volatile distribution and transport processes. Laboratory analysis of meteorites provides ground truth for remote sensing observations. By comparing spectroscopic measurements of asteroids with known meteorite compositions, scientists can establish links between specific asteroid populations and meteorite types. This connection enables detailed study of asteroid materials using sophisticated analytical techniques impossible to apply during spacecraft missions. The relationship between Earth and asteroids encompasses both existential threats and unprecedented opportunities. Near-Earth asteroids, defined as objects with orbits bringing them within 30 million miles of our planet's path, represent the most immediate concern for human civilization. Approximately 28,000 near-Earth asteroids have been catalogued, with new discoveries occurring daily as survey programs expand their search capabilities across increasingly larger portions of the sky. Asteroid impacts have shaped Earth's geological and biological history throughout deep time. The Chicxulub impact 66 million years ago created the Cretaceous-Paleogene boundary, ending the age of dinosaurs and enabling mammalian diversification. This 6-mile-wide asteroid released energy equivalent to billions of nuclear weapons, creating global environmental changes that persisted for years. Earlier impacts may have been even more devastating, with some scientists proposing that asteroid bombardment during the late heavy bombardment period 4 billion years ago sterilized early Earth multiple times. Modern impact monitoring focuses on potentially hazardous asteroids, objects larger than 460 feet in diameter, with orbits that could bring them within 4.6 million miles of Earth. These objects pose the greatest risk for regional or global catastrophe. The Tunguska event of 1908, caused by a relatively small asteroid or comet fragment, flattened over 800 square miles of Siberian forest. A similar impact over a populated area would cause massive casualties and economic disruption. The Chelyabinsk meteor of 2013 demonstrated that even small asteroids can cause significant damage without warning. This 65-foot object exploded in the atmosphere above Russia, generating a shockwave that damaged thousands of buildings and injured over 1,500 people with flying glass. The event highlighted gaps in current detection capabilities as the object approached from the direction of the Sun, where ground-based telescopes cannot observe. Planetary defense strategies encompass both detection and deflection technologies. The Double Asteroid Redirection Test, or DART mission, successfully demonstrated kinetic impactor deflection by altering the orbital period of Dimorphos, the small moon orbiting asteroid 65803 Didymos. This proof-of-concept mission showed that spacecraft impacts can measurably change asteroid trajectories, providing a viable defense option for future threats. Alternative deflection methods under development include gravity tractors, nuclear, standoff explosions, and solar radiation pressure enhancement. Gravity tractors would use spacecraft gravitational fields to slowly alter asteroid orbits over many years, suitable for small objects detected decades before potential impact. Nuclear standoff explosions could deflect larger asteroids by vaporizing surface materials to create thrust, though this approach requires careful analysis to avoid fragmenting the target into multiple dangerous pieces. Early warning systems rely on continued expansion of survey programs to detect threatening asteroids decades before potential impacts. The proposed near-Earth object camera would monitor asteroid populations from a Venus trailing orbit, providing better detection capabilities for objects approaching from the Sun's direction. Space-based telescopes offer continuous monitoring, without weather interruptions, and atmospheric distortion that limit ground-based observations. Asteroid mining represents the flip side of the threat equation, offering access to vast mineral wealth that could transform human space exploration. A single metallic asteroid contains more platinum than has ever been mined on Earth, while water-rich asteroids could provide hydrogen and oxygen for spacecraft fuel. The proximity of some near-Earth asteroids makes them more accessible than the lunar surface, requiring less energy for round-trip missions. Economic analyses suggest that asteroid mining could become profitable within decades as launch costs continue declining and robotic mining technologies mature. The first targets will likely be near-Earth asteroids containing water ice, which can be converted into rocket propellant for refueling spacecraft in deep space. This capability would enable more ambitious missions to Mars and the outer solar system by eliminating the need to carry all fuel from Earth's surface. Technical challenges for asteroid mining include prospecting, extraction, and processing in the microgravity environment. Unlike terrestrial mining, which relies on gravity to separate materials, space-based operations must use alternative techniques such as magnetic separation, electrostatic sorting, or chemical processing. Advanced robotics and artificial intelligence will be essential for operating mining equipment across the communication delays inherent in interplanetary operations. International law governing asteroid mining remains largely undeveloped, though the United States and Luxembourg have passed legislation recognizing property rights for extracted asteroid materials. The Outer Space Treaty of 1967 prohibits territorial claims on celestial bodies, but may not prevent resource extraction. Developing clear legal frameworks will be essential for encouraging private investment in asteroid mining. Ventures. Small-scale asteroid mining demonstrations may begin within the next decade. Several companies are developing technologies for prospecting missions that would identify high-value targets and test extraction techniques. These Pathfinder missions will establish the technological and economic foundations for larger-scale operations that could fundamentally alter humanity's relationship with space resources. The dual nature of asteroids as both threats and opportunities reflects humanity's expanding presence in the solar system. Effective planetary defense requires the same technologies needed for asteroid resource utilization, creating synergies between protecting Earth and expanding human capabilities beyond our home planet. The future of asteroid exploration promises revolutionary advances that will transform our understanding of these ancient worlds while establishing the foundation for human expansion throughout the solar system. Next-generation space missions, powered by innovative technologies and international collaboration, will unlock secrets preserved in asteroid interiors since the solar system's formation 4.6 billion years ago. The European Space Agency's Hera mission, launching in 2024, will conduct detailed follow-up observations of the DART impact site on Didymos. This investigation will measure crater characteristics, debris distribution, and long-term changes in the asteroid system's dynamics. Hera carries 2 CubeSats that will perform close proximity operations, demonstrating autonomous navigation technologies essential for future asteroid missions. The mission will establish whether kinetic impactors represent viable planetary defense options for various asteroid types and impact geometries. NASA's Psyche mission targets one of the most intriguing objects in the asteroid belt, 16 Psyche, a metallic asteroid that may represent the exposed core of a differentiated planetesimal. Launching in 2023, Psyche will use advanced instruments to map the asteroid's composition, magnetic field, and internal structure. This mission could provide the first direct observations of planetary core material, offering insights into how terrestrial planets formed and evolved. During the solar system's chaotic early history, advanced propulsion technologies will enable more ambitious asteroid missions with greater scientific returns. Solar electric propulsion systems, demonstrated successfully by the Dawn mission, will power larger spacecraft carrying more sophisticated instrument suites. Nuclear thermal propulsion, currently under development, could reduce travel times to the outer asteroid belt from years to months, enabling multiple asteroid visits within single mission lifetimes. Artificial intelligence and machine learning will revolutionize asteroid exploration by enabling autonomous operations across communication delays that make real-time human control impossible. Future spacecraft will independently identify interesting surface features, adjust observation strategies based on preliminary results, and even modify landing sites to avoid hazards. Deep learning algorithms trained on terrestrial geological datasets will help interpret alien landscapes and identify targets for detailed study. Swarm robotics concepts envision deploying multiple small spacecraft to simultaneously explore different aspects of asteroid systems. Individual CubeSats could specialize in specific measurements, composition, magnetic fields, internal structure, or surface geology, while sharing data through mesh networking protocols. This distributed approach provides redundancy against single-point failures, while enabling comprehensive characterization of asteroid systems at lower cost than traditional large spacecraft. Sample return missions will expand beyond simple surface collection to deep drilling and subsurface exploration. Advanced drilling systems could penetrate hundreds of feet into asteroid interiors, accessing materials unmodified by space weathering or cosmic radiation. Cryogenic sample storage will preserve volatile compounds that would be lost during room temperature return journeys, maintaining pristine records of early solar system chemistry. The asteroid impact mission concept proposes deliberately crashing large impactors into selected asteroids to expose interior materials for spectroscopic analysis. High-speed impacts would create temporary excavations, revealing subsurface compositions, while generating ejector plumes containing pristine interior materials. Observing spacecraft would analyze impact-generated spectra to determine three-dimensional compositional structures impossible to measure through surface observations alone. Human asteroid exploration represents the next logical step in space exploration, combining robotic reconnaissance with human adaptability and real-time decision-making capabilities. Near-Earth asteroids provide accessible targets for human missions that require less energy than lunar expeditions, while offering unique scientific and resource utilization opportunities. Astronaut geologists could identify and collect samples based on field observations impossible to replicate with robotic systems. Asteroid bases could serve as stepping stones for human expansion to Mars and the outer solar system. These installations would provide staging areas for deep space missions, while developing technologies for living and working in low-gravity environments. In situ resource utilization at asteroid bases would produce fuel, water, and construction materials from local materials, reducing dependence on Earth-supplied resources. Commercial asteroid mining ventures will likely begin with water extraction from near-Earth asteroids, providing propellant for satellite servicing and space tourism operations. As technologies mature and markets develop, mining operations will expand to include rare earth elements, platinum group metals, and other materials with high terrestrial value. The asteroid belt's vast mineral wealth could support human civilization for millions of years. Terraforming applications may eventually utilize asteroid materials to modify planetary atmospheres or create artificial habitats. Water-rich asteroids could provide hydrogen and oxygen for breathable atmospheres, while rocky asteroids could supply construction materials for space habitats. The combination of abundant materials and low escape velocities makes asteroids ideal sources for large-scale space construction projects. Long-term exploration goals include comprehensive mapping of the asteroid belt's structure, composition, and evolutionary history. Systematic surveys using advanced space telescopes will identify millions of additional asteroids while characterizing their physical and chemical properties. This cosmic census will reveal how gravitational forces, collisional evolution, and thermal processing shape the solar system's architecture over billions of years. The ultimate frontier may be asteroids in other star systems, detected through gravitational microlensing and direct imaging techniques. These distant worlds would provide comparative planetology opportunities, revealing whether asteroid belt formation represents a universal process or unique circumstance. Future interstellar missions might target asteroid-rich systems as the most accessible destinations for humanity's expansion to the stars. Through continued exploration and technological development, asteroids will transition from mysterious dots of light to familiar worlds supporting human presence throughout the solar system. These ancient time capsules will continue revealing secrets about cosmic origins while providing the resources necessary for humanity's transformation into a spacefaring civilization.